In this video, we will introduce capacitors. This is the beginning of our transition from static arrangements of charges to circuits, where we will have currents flowing. Capacitors make a nice bridge topic because you can consider them in the static case when there are static charges on the capacitors, but capacitors are still useful in circuits where current is flowing and charges aren't stationary. We'll see that in more detail in the future. For now, what is a capacitor? A capacitor is an object, usually two conductors, that you can connect to a circuit. When you apply a potential difference across a capacitor, it begins to accumulate and store charge. There you have it. It's a device that stores charge. This is useful because it not only stores charge, it stores energy. And when you want a lot of energy very suddenly, what you can do is discharge a capacitor. For example, the flash in a camera is often powered by a capacitor. You charge up a capacitor and then let it discharge through the flash. It gives a sharp pulse of energy, a sharp pulse of light. Typically, a capacitor will consist, as I said, of two conductors. One will end up with positive charge and the other with negative charge, and they will both have the same magnitude of charge. So one is plus Q and one is minus Q. And there will be an electric field established between them. We know that wherever there's an electric field, there must be a potential difference. And we define the capacitance simply by the ratio of the charge stored Q over the potential difference delta V. Now, notice that the capacitor as a whole remains neutral because you have plus Q on one and minus Q on the other. But to define the capacitance, we just take the magnitude of one of those Qs and divide by the magnitude of the potential difference. And capacitance is always a positive number, and it is measured in units of farads, named after Faraday. One can actually talk about the capacitance of just a single conductor. All you need is something that stores charge. So you could put charge on a single conductor and talk about the potential difference between that conductor and infinity, and use that for your delta V. And then the charge Q over delta V would give you the capacitance of that single conductor. But in practical circuits, in most cases, capacitors have two plates, two conductors. The simplest type of capacitor has two large parallel plates. If the separation between the plates, which we'll call D, is much smaller than the area of the plates, then for most of the points between the plates, you can consider those plates, they're so large that you can consider them to be infinite. And so you get a very nice uniform electric field between the plates, because we know that the electric field due to an infinite sheet doesn't depend on distance and is nice and uniform. And to a good approximation, that is what is happening between the plates of a capacitor. So if you want a nice, large, uniform electric field, you basically use capacitor plates and charge them up. We can use what we've learned before about electric fields and potential to figure out the capacitance for a parallel plate capacitor. So, for example, we know that on one of the plates, if you have a charge Q spread over an area A, spread uniformly, then we can talk about the charge density, the surface charge density, sigma. We know that the electric field between the two plates is going to be of magnitude sigma over epsilon naught. If it was just one plate, it would be sigma over 2 epsilon naught. But both the positive and negative charges contribute to a strong field in the same direction when you're between the plates. And so we have sigma over epsilon naught is the strength of the field between the plates. We also know that the strength of the electric field is related to the gradient of the potential, that is how quickly potential changes with position. So in other words, the magnitude of the electric field is roughly delta V over delta X. Now, technically what we want here is a derivative, but if you have a nice constant electric field, then the derivative could be replaced by delta V over delta X. But remember, this is only true in the case where you have a nice constant electric field. In this case, though, since that is what we have between the two parallel plates, we can say that the electric field strength is delta V over the distance between the two plates, which is D, the separation between the two plates. Putting that all together, we defined capacitance as Q over delta V. We can plug in for Q as sigma times A, and we can plug in for delta V as the electric field strength times D, the separation. We already know that the electric field strength is sigma over epsilon naught, so we plug that in and cancel and simplify to get the capacitance of a parallel plate capacitor. That's what the PP is standing for here. The capacitance of a parallel plate capacitor is epsilon naught times A divided by D. Now, of course, there are many other types of capacitors. For example, you could have a spherical capacitor where both the plates are spheres and concentric spheres, one inside the other, and one is positive and the other is negative. There would actually be a tiny little hole so that the wire connecting to the inner plate could come in, but it would be insulated so it wouldn't make contact with the outer plate. And the capacitance of a spherical capacitor would be given by this formula. And again, you can see that if the separation between the plates is small, if B minus A is small, then you get a large capacitance. You could have a cylindrical capacitor where you have two concentric cylinders. And again, you can see that, oh, if the ratio B over A is close to 1, right? If there's not much separation between them, then you get log of a number very close to 1 will be very close to 0. Log of 1 is 0. And so number close to 1, you have log of that number will give you a number close to 0. And you're dividing by a very small number means you get a large capacitance. So again, we see this pattern of, oh, if the plates are close together, the capacitance increases. Another way that you can have a large capacitance is by having a large area. If we quickly skip back for a moment, so you can see here that, yes, if you decrease the distance, then you increase the capacitance, or if you increase the area, you can increase the capacitance. And so to build a capacitor with a large capacitance, you want a large plate area and a very small separation between the plates. And so one way that they used to do this was the jam roll method of constructing capacitors. They would basically take very thin foils and layer them. So you can see here, okay, we have an electrode, we have the separator, which we will talk about dielectrics in a bit. But basically this made sure that two conductors didn't touch each other. And then the other electrode, and then another separator, and then you just roll it all up so that it looks like a jam roll. So in cross section, you would see a jam roll like this. And so this has the advantage of having a large plate area, but contained inside a small volume and with a very tiny separation between the plates. These days, they get even better capacitances by using a foam structure, because foams typically have very large surface areas. So they create a foam structure and again, coat it in multiple layers, alternating between conductors and insulators. And that gives a very large capacitance. So we notice that the value of the capacitance only depends on the geometry of the capacitor. It doesn't depend on the potential difference you're applying. As you increase the potential difference, the charge stored will also increase, so that ratio Q over delta V will stay the same. And we have seen that it depends only on the geometry of the plates. How large are the plates? How close are they together? What shape are they? And so on. And we have seen already from the formulas that we can increase the capacitance by increasing the plate area. And thinking in terms of Q over delta V, This makes sense because the larger the plates, the more charge they can store for a given potential difference. So increasing the plates allows you to store more charge for the same potential difference. So that increases the ratio of Q over delta V. And so it increases the capacitance. You can also increase the capacitance by decreasing the distance between the plates. Intuitively, this makes sense because the closer the plates are, the easier it is for the positive charges on one plate to attract the negative charges on the other. And so you can store the same amount of charge with a smaller potential difference. So you have the same amount of Q, but a smaller delta V, you've increased the capacitance. Let me note here that the electric field between the plates only depends on the surface charge density, sigma. So as long as the amount of charge on each plate stays the same, the electric field will stay the same. But here we can see that if we decrease the separation, even if the amount of charge stays the same and the electric field stays the same, since the electric field lasts for a shorter distance, since the separation is decreased, the potential difference will be smaller, which makes sense because we can relate E times D to delta V. The third way we can change the capacitance of a capacitor is by inserting a dielectric between the plates of the capacitor. So we go from the case where there is a vacuum between the plates of the capacitor, where for a parallel plate at least, we have CPP is equal to epsilon naught A over D, to the case where we have filled the space between the plates with a dielectric. And now the capacitance is given by kappa times epsilon naught A over D. The K looking symbol here is kappa, Greek letter kappa. And in this context, it is called the dielectric constant. The dielectric constant only depends on the material that you use. Because we don't want the charge to actually flow from one plate to the other and discharge the capacitor, the dielectric will be an insulator, not a conductor. Each insulating material will have its own dielectric constant. So you could use glass or mica or a variety of other materials. To give you an idea of some typical numbers, Teflon has a dielectric constant of 2.1, paper about 1.4, mica somewhere between 3 and 6, silicon dioxide, silica, about 3.9, rubber, about 7, salt, somewhere between 3 and 15, and then going up to the higher end, strontium titanate has a dielectric constant of about 300, barium strontium titanate can go up to 500, and various other materials can go as high as 100,000 and so on. The dielectric constant is unitless, which makes sense. We already have all the units we need from epsilon naught A and D. Kappa is just a multiplicative factor. I also want to note that sometimes people will combine kappa and epsilon naught and call it a new constant, epsilon. And epsilon has the name, the permittivity of the material. In fact, now this allows us to see why epsilon naught has the name permittivity of free space. This is the permittivity you get when there is nothing but vacuum or free space between the plates. It's the OG epsilon, if you will. How does a dielectric help increase the capacitance? We know that a dielectric will have polarized molecules inside it, and that when we place it between the plates of the capacitor, it gets exposed to an electric field. This electric field polarizes the material and makes all the dipoles align with the electric field. But in the process, because each of these polar molecules has their own little electric field, they help neutralize the electric field between the plates to some extent. A conductor would completely cancel out the electric field inside the material. But we've seen already that conductors have the problem that they would also neutralize the charge, allowing it to flow from one plate to the next. So dielectrics instead, even though they don't completely eliminate the field, they reduce it a lot and leave the charges where they are. We know that in the context of this parallel plate capacitor, that delta V is equal to E times D. Since the magnitude of the electric field has decreased, delta V will decrease. And since C is equal to Q over delta V, that means that the capacitance has increased. So the better a dielectric is at reducing the electric field, the greater an effect it will have on the capacitance. And finally, just a note on units, capacitance is measured in farads. And as we can see, since C is equal to Q over delta V, a farad is equal to 1 coulomb per volt. The farad is named after Michael Faraday, an extremely interesting figure who didn't have much formal education, but went on to make major contributions to the study of electromagnetism.